Today, we want to take another look at linear functions. Yesterday, we had an example of a linear function. If you would recall, I don't want to replicate the entire table. Z is equal to 5 plus 2/3 x minus 1/4 y. We have to type this in a single line. Speaking of pedantic communication, in single line syntax, if I say on a Canvas version of this, and I ask you to type the equation of the line, sorry, the equation of the plane, and we have to use single line syntax. Notice that I've got these fractions. These fractions are coefficients, and they're going to need parentheses. We're going to make sure that there's no question that the 2/3 is being multiplied by x. So we're going to write z is equal to 5 plus 2/3 x, and then we're going to be efficient and say minus 1/4 y, rather than saying plus parentheses minus 1/4 close parentheses y. This will make sure that whoever looks at this understands what you're trying to communicate. Remember, the thing that is looking at this is going to be Canvas. A computer is going to be looking at this. Computers are very, very dumb, and they won't understand any kind of nuance. My computer's going to mess with me later on because of that. But, good. I put tape over the camera so I could flip it off. I'm just kidding. There's no tape on the camera. I want it to know. I'm just kidding. I don't abuse my elders. This is a very old computer. So our single line syntax, we're going to make sure that our coefficients are in parentheses. But we don't want to do that elementary algebra stuff where we have to put plus, minus in the parentheses. All right. So we've had, the way we were thinking about this is we think about z equals 5 makes a flat plane. And then when I write plus 2/3 x, that gives the change in z in the x direction will increase by 2 when x increases by 3. So the plane tilts up in the x direction. And then I tilted the plane down in the y direction with a slope of negative 1/4. So I just took this plane and dropped it down negative 1/4 and gave it, so up in the x direction, down in the y direction. And we could see how much it was changing in each of those. So this 2/3, was one of our slopes. The change in z with respect to x. So the change in z is in the x direction. Every row on that table, we saw that z increased by 2 whenever x increased by 3. That was all the rows on the table. In the table, on the table, in the table. Each row in the table, z increased by 2 when x increased by 3. Negative 1/4 was the change in z with respect to y. This is what was going on in each column of the table, because I listed all the different y values. I fixed the x values and changed the y values in each column. So each column of the table z decreased by 1 when y increased by 4. That's what we saw happening in the table. in each row. Z increased by 2 when X increased by 3. So our slope in the X direction, our dz dx, was 2/3. Our slope in the Y direction, our dz dy, was negative 1/4. Any questions? Here's the memory that this should tap into, even though we haven't brought it up yet. I have slope and I wrote it delta z over delta x, but I said dz dx because eventually these changes are going to get very small. And instead of finding slopes with secants, we're going to be finding slopes with tangents. So these are future derivatives. There's 2 of them, and we're only considering how z is changing in the x direction and the y direction. So we're going to call them partial derivatives. These are future partial derivatives. All this talk about slope should make you think of derivatives because we are in calculus class. There they are. Eventually our dz, our delta z over delta x is going to be the infinitely small dz over dx. How's everybody okay? I asked a follow-up question. Oh, now I need points. Which was find a vector normal to the plane. A linear function in 3 variables will be a plane in R3. And one of the things that we care about is a vector normal to the plane. And there were 2 things that we could do. Part B said find a vector normal to the plane. And I saw 2 approaches, which are the 2 approaches that I was thinking of. So here are the 2 approaches that I saw yesterday. 1, write the equation in standard form. The coefficients of the variables will be the components of a normal vector. The coefficients in standard form are the components of the normal vector. So if we take this equation and rewrite it in its standard form which would be all the variable terms on one side and constant terms on the other, or some minor variations of that. So if I write the 2/3, I put a negative 2/3 x plus 1/4 y plus z, that was just still there, is equal to 5. So if we rewrite this in the equation in standard form, the coefficients of the x, y, and z will be the corresponding components of the normal vector. I didn't say this, so if you're like, oh, when did you say that? I did not. Some of you read about it, some of you knew it already, and so that was cool. So we could say that a normal vector I didn't want to make it a unit vector, but a normal vector could just be negative 2/3, 1/4, 1. This might not be the one that you came up with, even though I told you it was correct. You just had the one that was 12 times as long as this one. If you multiply everything by 12, you multiply this by 12, this, because I wanted to clear out the denominators. And this will make it look like the cross product that you might have got. These two vectors are in the same direction. They have different magnitudes. The second one is 12 times as long as the first one. I shouldn't give them the same name. Very George Foreman situation right now going on right here. N2 is just 12 times as long as N1. And it doesn't have any fractions in it. So all you fraction haters will prefer N2. Some of you knew that we could go after the coefficients in the standard form to get the components of a normal vector. This is going to take some more examination. We're going to have to see if this part is backwards compatible. The other thing that you could do, your other option, was to find find the cross product of two vectors that are in the plane. So another thing that you can do is find the cross product of two vectors. Oh, I didn't say everything I needed to say. I just was not pedantic for a moment. What did I forget to say? Any two vectors cross product? Non-collinear vector, linearly independent or non-collinear vectors. So I need two non-collinear or linearly independent vectors. They can't be going in the same direction. Because if I just have one vector, there's a whole plane perpendicular to that. But if I have two non-collinear vectors, two linearly independent vectors, those two are defining a plane, and there will be one vector perpendicular to both. In R3. In R4, we got a whole plane perpendicular. Much more space here. The issue that we have here is that what we have is a collection of points. And so grab 3 points and turn them into vectors. So you can use 3 points to find two vectors. So for example, I picked P is 0, 0, 5. I picked stuff that had lots of zeros in it, as many zeros as I could get. And then I just subtracted to find a direction vector from one point to the next. So I did 3 minus 0, 0 minus 0, 7 minus 5. And then I did PR. Zero minus 0, 4 minus 0, 4 minus 5. And then found the cross product of those two vectors. I can show you what I wrote down because I saw some other people had the same answer. So what I usually do is write down my answer, then look around, see if it agrees with y'all's answer. And I go, okay, I must have done something right. I know I can probably verify my answer and then react to yours, but it's much easier to predict. Reacting is very expensive, metabolically speaking. Predicting is easier. That's why we do it so often. Any questions? Yes. That's a great question. How does the first approach work? Secretly, we already knew this first approach. Just no one ever pointed that out before. So let's think about this first approach in terms of a line. So let's think about this first approach in terms of this line, y equals mx plus b, or alternately described as y equals ax plus by equals c. This point slope intercept, and the standard form. And let's see what a and b are telling us. So I'm going to break the slope of m into a rise and a run. So I'm going to write y is equal to b plus rise over run times x. And then I'm just going to rewrite this in standard form. I'll put the rise over run on the other side. Actually, I'm going to multiply by run first. Multiply through by the run, just to make the a and b really stand out. And then move the x term over. So that'll be a negative rise plus the run is equal to whatever the run is times b. This corresponds to ax plus by equals c, where the coefficient of x is the opposite of the rise, and the coefficient of y is the run. Or if we multiply by -1, a is the rise and b is the opposite of the run. The change in y is getting multiplied by the x. The change in x is getting multiplied by the y. Feels weird, but all right. Let's look at a number example. If I write this equation in in standard form, we'll multiply by 3 and subtract 2x. We'll get -2x plus 3y is equal to 15. Let's draw the line with the slope of 2/3. We'll start off 5. And we'll do a rise of 2 over a run of 3. I'll do the opposite too, a rise of -2 and a run of -3. Now I'm going to look at the vector whose components are the coefficients in standard form. I'm going to grab the vector. I'm going to grab the vector with the coefficients that whose components are the coefficients in standard form. So -2, 3. I'm going to draw that vector along with this line. What is going to happen? Predict. This is one of the cases where predicting is going to be more energy than reacting. What's going to happen? What is this vector going to be relative to this line? How are they going to look? Not the same. What did our experience in the previous problem tell us? Not quite. Although that's a great observation. Last time I multiplied by 12 to get rid of the things. Here I have to multiply by 3 to get rid of the denominators. So that's good. Some people did it already, which is how I know you did the hand sign. Some people were giving me the Ultraman. Does everybody know who Ultraman is? I've referenced that before. Know who Ultraman is. Let's draw the vector -2, 3. So I'm going to pick a point. I'm going to just start here at 0, 5. And I'm going to go -2, +3. So there's the vector -2, 3. What's the relationship between the vector and the line? Another way we could think about it is, what is a vector that describes the original line? 2/3 is the slope. That's how we normally describe slope, with one number, the change in y divided by the change in x. But a vector, if I wanted to describe this with a vector, that vector, the run is 3 and the rise is 2. So what we notice about this vector made up of the components, or sorry, the coefficients, whose components are the coefficients of the standard form, that vector is perpendicular to our original line. That is normal to the line. Our line is 5 + 2/3 x. When we rewrite that in standard form, I get -2, 3 for the coefficients. Those are the components of a normal vector. This is exactly the same thing what we did yesterday, what some of you did yesterday when you rewrote the equation in standard form. Any questions? The only difference is, instead of just being y = 5 + 2/3 x, we had z = 5 + 2/3 x minus 1/4 y. Rewrite that, get the components of a normal vector. This works even in R4. If we had a 4-dimensional space, this is where we would need something like this. Because in 4-dimensional space, in R4, we no longer have the cross product available to us. But if I take x4 is equal to 5 plus, I need 3 variables. It's going to be too complicated. Yeah. W equals constant plus first slope times x plus second slope times z plus third slope times y. If I rearrange that into standard form, I'll have a 4-component vector, one vector in R4 that will be perpendicular to the 3-dimensional solid described by the equation. The coefficients of standard form are the components of the normal vector. Yes. I just multiplied by 3. So 3y is 15 plus 2x. And then I put the 2x on the other side. So minus 2x plus 3y is 15. And then for the vector, I just grab the coefficients, which is what we were doing yesterday to find a normal vector. That grab the coefficients of the standard form is not unique to R3. It also works in R2. Any questions? Like I said, the stuff that when we start using words, they have to be consistent in what they mean. But this is math. Sometimes we duplicate notation. We use the same notation to mean different things and hope that the context is clear enough. I'm looking at you, interval notation. How's everybody okay? Every once in a while, we have to go through and we have to clean up our language. Here's what I mean by that. If I take 4/6, what's the equivalent fraction? What's this equal to? 2/3. For those of you who are like, oh, I don't know, it's an uncountable infinity of things. I'm like, oh, you know which one I'm talking about. What process is this? What is this process called? How many of you are like, oh, you simplify the fraction? How many of you were told the word, you simplify the fraction? Now I want to find out how old your previous math teacher was. How many of you said, reduce the fraction? That's good. You had younger math teachers. You have to be my age. We used to say, reduce the fraction. And then finally someone said, the fraction is the same. There's nothing smaller about it. You know what I mean? Because we used to say reduce when we said reduce to lowest terms. But then that was too much of a phrase. So we just started saying reduce. And then someone said, that is terrible. That's terrible because it kind of sounds like the fraction is getting smaller. It's like, oh, no, 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 we're reducing the parts. It's like, oh, no one is going to interpret it that way. They're going to be like, oh, the fraction ain't getting smaller. The hell, man. So then we went with the word that we already had, simplify. Michael, why don't we just call it what it is and say simplify? And then a bunch of old math teachers like, oh, I don't want to change. And it's like, oh, then retire. And they're like, oh, no. Which is fair. They couldn't afford to. Because we already had things like simplify, right? We already had things like simplify. So let's just use that language. Do we all agree? Everybody agree with what I wrote? What I wrote is correct? What I wrote is correct? You can tell the answer is no just by the way I'm asking the question. Why is this not correct? This isn't true. This is not true. Yeah, it depends on the value of x. When is this not true? When x equals 3, then this is not true. So to make this correct, I'd have to be like, oh, when x is not 3. Any questions? So the coefficients in the standard form tell us the components of the normal vector. The next thing we need to talk about, since we are now talking about surfaces, a function of two variables will produce a surface in R3. We started off with our simplest surface, just a nice plane. Start with a flat plane parallel to the XY plane, and then add some change, some slope in the X direction, add some slope in the Y direction, new plane. We need a way to picture what's going on. We need a way to visualize changes in height when we're going to represent things on a flat surface, because we don't yet have like little mini holograms where we pull out our phones and they produce little holograms that we could turn around and spin around. I know you think that there's like 3D stuff. It's like, oh, the Wolfram Alpha makes 3D maps. Michael, really? How many dimensions are you looking at again? How many dimensions are you looking at again? Your brain is putting that together. You're not actually looking at a 3D thing, right? Doom 3D was a lie. It was lying to you, and your brain was just going along with it because you got to shoot demons and stuff. So, I mean, win-win. So for contours and level curves, this is a way that we can picture a surface with a two-dimensional representation. So picturing we want to be able to picture a two-dimensional surface in R3 on a plate. So our strategy is to do the same thing that we always do. Take our new problem and reduce it to an old problem. Take the new problem, turn it into an old problem. So rather than trying to picture this surface z equals f of x, y, I just pick a bunch of values for z, like k, a bunch of different values of k. And now I'm looking at an equation with just two variables in it, which is a curve. We'll have a bunch of equations in two variables for different values of k. And an equation in two variables will be a one-dimensional curve in R2. Those of you familiar with the concept, this is just a topographical map. So that's what we want to think about next. We need to build a library of surfaces where we look at an equation and we can imagine what the surface looks like. We need to build a library of surfaces that we can picture. Just like you've got a whole library of functions running around in your memory. Y equals mx plus b, you're picturing a line. Y equals ax squared plus bx plus c, you're picturing a parabola. Y equals square root of x, you're picturing half a parabola. Y equals sine x. You have a whole library of curves that you remember. Now we just need to have a whole library of surfaces that we remember. Right now we've got planes and we're just going to build on that. Any questions? Comments? Sniper ones? How's everybody okay? Dope. Tomorrow we'll talk about contours and level curves, and we'll start building that library of surfaces that we recognize. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.